Our next problem will be a little bit different. This time we will have infinitely long straight wire with current I, and this current I will be changing in time. It will be equal to I naught, which is constant, times cosine omega t, where omega is also a given constant. And then we will have a circuit, and this circuit has zero resistance. Zero resistance. It's given that resistance of this circuit is zero, but it has a capacitor with capacitance C. This circuit has certain dimensions that are given. This distance is h. This distance is d. And this distance is w. One more time, the circuit has no resistance and its self-inductance can be ignored. Find the charge on the top plate of this capacitor as a function of time. Find the charge on the top plate of this capacitor as function of time. First question, which law we will use? So let's think about it. First of all, why will we have current here? Well, we have this wire with current I. This wire with current I will generate the magnetic field, and we will use Ampere's law, integral B dot dr is mu naught I, to figure out what is the magnetic field created by this current. And when we find this magnetic field, we will realize that since current is function of time, then the magnetic field will be function of time, which means that there will be non-zero flux of the magnetic field in this circuit that will generate current through this loop, through this circuit. So we will use also Faraday's law to find out what is the charge on the top plate of this capacitor. So it is minus d dt integral B dot ds, flux, time, change of the flux of the magnetic field in time, and minus comes from Lenz's law. All right, so let's follow the steps. First of all, let's find the magnetic field created by this current. The lines of the magnetic field will be circles. They will be at each point parallel to dr. So I take b out of this integral. B 2 pi r circumference is equal to mu naught current enclosed, which is I naught cosine omega t. So the magnetic field B is mu naught I naught cosine omega t divided by 2 pi r. Now we need to find out the direction of the magnetic field. To find the direction of the magnetic field, you use your right hand. I use my left hand because you see my mirrored image, but you take your right hand, you put your thumb along current, you grab the wire, and here below this wire, your fingers go into the page. So the magnetic field in the region that we are interested in below the wire is into the page. B is in, and I add the direction here. Okay, so now we know that we have the magnetic field that changes with time. So next step is to find the current and to find the charges on the capacitor using Faraday's law. And as always, we follow the steps. So step number one, I choose before we even follow the steps, let's find the direction of current. Well, we see here cosine. So let's just think about the interval when omega t changes from 0 to pi over 2, which means that cosine changes from 1 to 0. So cosine decreases, B decreases, magnetic field, the external magnetic field decreases, which means that flux decreases, which means that B self-induced will be in the same direction as the original magnetic field. So we need to have B self-induced magnetic field in the same direction as the original magnetic field to oppose the change of flux, since flux decreases. Okay, to have B self into the page, we need to use right hand to find the direction of current. If B self is into the page, I put my thumb along direction of B, I bend my fingers, and we see that the direction of current has to be clockwise to satisfy this requirement that B self is into the page. So the direction of current is clockwise, and I will call this current I tilde to make difference between this current in this loop and this original current in the infinitely long straight wire. Then we understand that magnetic field, since we have cosine here, magnetic field then will be increasing, decreasing, so direction of current will be changing. But we just start with something. We worked with omega t that was changing from 0 to pi over 2 to figure out the initial direction of current, and we will stay with it. So what are the next steps? We follow the steps, and our first step, as always, is to figure out the direction of dr or direction of ds. So as always, I follow the convention. I go around the loop in counterclockwise direction, and my thumb shows me direction of ds. So this is the way we go around the loop, which makes ds out of the page. Okay, first was direction of dr and ds that follows from dr. Second step, what is our second step? Second step is to find the flux of the magnetic field. But before we do it, we have a capacitor here. So we found out direction of current. We need to make a decision which plate is positively charged and which plate is negatively charged. Well, I choose something. So current comes here. Why don't we choose low plate to be positively charged and upper plate to be negatively charged? We make our choices and we stay with them. Our next step is to find the flux of the magnetic field. Phi is integral B dot ds by definition. Now let's look at this. B, which B we care about? Which B is this B? I remind you that they told us to neglect self-inductance, so I use this B self just to find the direction of current. I don't need it anymore. So since we neglect it, what we care about is the external magnetic field. Direction of external magnetic field is into the page. ds is out of page, so B dot ds is negative. I put minus. Then integral B is right here. It is mu naught I naught cosine omega t divided by 2 pi r. This is B. The question is, what is ds? We already solved this similar problem. We understand that since B is changing, we need to integrate. We need to write ds as the area of this stripe that has this dimension as w. ds is w, but this dimension is dr, because as we see, magnetic field is changing with r. The further you are, the smaller is the magnetic field. Let me finish. ds is w dr, so this part is ds. And we don't forget the limits. What are the limits of integration? We go from h to h plus d. To h plus d. Okay. We keep going. All these are constants, so it is minus mu naught I naught cosine omega t divided by 2 pi, and w. And then look what we have. We have dr over r, which is logarithmic function of r. Logarithmic function, let me bring h a little bit up. Logarithmic function of r. And the limits are from h to h plus d. So it is minus mu naught I naught cosine omega t, then w divided by 2 pi, and then logarithmic function h plus d over h. We found the flux. What is our next step? Next step is we need to find d phi dt. And I'm running out of space. I need to erase something. Our next step is to find d phi dt. What is d phi dt? It is minus mu naught. All these are constants with respect to time. Mu naught, I naught, then w, 2 pi, and then logarithmic function h plus d over h. The dependence on time is here in this cosine. Derivative of cosine is minus sine, so minus and minus plus. And then I write sine omega t. Derivative of cosine is minus sine omega t. And then I use chain rule, and I get omega here. All right, we found d phi dt. What is the next step? Next step is to work with the left-hand side of Faraday's law. We need to find integral E dot dr. Integral E dot dr is minus d, let me put it here, d phi dt, since we already wrote phi. Okay, what is integral E dot dr? I remind you that what was given in the problem, they told us that resistances of the circuit is 0. All we have is capacitance. We go around the loop. We come here. We go in counterclockwise direction. We go down. dr is down. Electric field from plus to minus is up. So E dot dr is negative. I put minus. What is the change in E dot dr? What is magnitude of this change? Magnitude of this change is Q over C. And we are done with the left-hand side of this equation. Since the resistance is 0, we have nothing else in this capacitance, and we neglect self-conductance. Okay, so it is equal to minus. This minus, never forget it. Minus from Faraday's law. And then I have d phi dt right here. Mu naught I naught w over 2 pi. Logarithmic function h plus d divided by h omega sine omega t. And look at this. Now we can solve for Q. I erase Ampere's law that we I erase magnetic field that we already used, and we will write the final answer. Q. I remind you that this Q is the magnitude of the charge here. We already took into account that it is negative. We put negative sign here. That was our choice. So this Q is positive, and it makes perfect sense. Positive Q, well, magnitude Q here is mu naught. Let me start with C. I bring C here. It is C, capacitance. Then mu naught I naught W over 2 pi. Logarithmic function h plus d over h, omega, and then this is omega, and then sine omega t. So look, we found the charge on the plate of this capacitor, and since we have here sine omega t, it will be oscillating with time.